Hello, today we're going to talk about odd and even functions. Odd and even functions. But before we get on to that, let's refresh our memory as to some of the most basic graphs. If your function f of x is just plain old x, it's going to look like this. It's going to be a diagonal line soaring upwards into the first quadrant. If your function, your f of x, is negative x, it's going to look like this. It's going to be a graph with a diagonal line descending into the fourth quadrant. If your function, your f of x, is x squared, it's going to look like this. It's going to be, well, I like to think of it as like a smile. It's going up like that, and if your f of x is equal to negative x squared, well, it's going to be the same thing flipped over. It's going to be, instead of looking like a smile, it's like a frown. And the way I remember which one is which is, if you're negative, you tend to be very sad. So this negative function here has a big frown, but this positive x squared function is a happy smiling one. Then we've got function f of x, which is equal to x cubed. And a function like this is going to look, well, it's going to look a little bit like your digestive tract if you've got a very vivid imagination. And if your function, your f of x, is equal to negative x cubed, it's going to look like this, more or less. Sorry, it's a little bit imprecise. I'm doing this freehand. Okay, now the question is, which of these functions are odd and which of them are even? Well, we're going to find out what that means. I'm assuming at this point you've seen the functions. I mean, you've got a basic knowledge of what these fellows do. Now, the parade example of an even function is f of x is equal to x squared. That's the one that looks like this. And they generally explain this by saying the graph is symmetric around the y-axis. There's the y-axis, this is the x-axis. That means whatever you've got here is reflected like in a mirror over here. And a more algebraic way of describing that is to say that f of x is equal to f of negative x. Now that's very abstract. Let's take a concrete example. Then if we use 2 as the value of x, then we've got f at 2, which is equal to 2 squared, which is equal to 2 times 2, or 4. So if the x input value is 2, we're going to get a y height, a y output value of 4, right about here. But if we put in a negative value for x, put in the same value for x, but make it negative, f of negative 2, that's going to be negative 2 squared, which is negative 2 times negative 2, which is equal to, well, 2 times 2 is going to be 4, and a negative times a negative is a positive, so we're going to just leave that as it is. So we've got a 4 over here. If we put in a negative 2, we'd still get a y height of 4. So both of our y outputs, as the graph shows, have a height of 4. So we've got a 4 when we put in a positive 2, we got a 4 when we put in a negative 2, and that's the meaning of this. F of x is equal to f of negative x. If we put in the same value in a positive form and a negative form, we're going to get the same outcome, even though one is positive and one is negative. And this would work for any number you put in there if you've got an even graph. Looking back at our first page, we see that x squared here is symmetric around the y-axis, and that's the one we just discussed. So that's definitely an even function. And even when we use the negative form of it, we're going to get the same result. If we put in a -1, well, if we squared -1 times -1 would be +1, but we've got a negative sign in front of it, so that would give us a y height of -1 down here. And if we put in a +1 right over here, it would be 1 squared, that's still 1, but -1 squared, -1, that would still be a negative height. So we'd get the same result, whether we have a positive input here or a negative input, we would have the same output. So because f of x is equal to f of -x, whether the input, as long as it's the same, is positive or negative, you're going to get the same output. You've got a symmetric, around the y-axis, even function. So this is even, and this one here is even too. And by the process of elimination, you've probably guessed that these other four are all odd functions. But let's find out exactly why that is the case. Now, for an odd function, let's take a classic one. F of x equals x cubed. And if you put that in your graphing calculator, you'd end up with a graph which looked pretty much like this. Now, an odd function is symmetric around the origin. That's a rather difficult expression to understand. What that means is if we took this part of the graph over here, if we flipped it over to this side and then flipped it down, if we flipped it over here and then flip that down, it would match this side. So we have a clearer view of our original graph. So yes, so if we flip this over to here and then flipped it down, it would match up with this. Now what that means is we've still got a kind of symmetry here, but it's not the kind of simple symmetry we had before with an even function like x squared. When you put in a -2, you got a 4. When you put in a +2, you got a 4. But here, something different is going to happen. Let's take an example, because that will be much easier to follow. Let's say we put in f at 2. Well, that's going to be equal to 2 cubed, which is 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, so that's going to be equal to 8. But if we put in f at -2, that would be equal to -2 cubed, which is -2 times -2 times -2, which is equal to, well, 2 times 2 is 4, times 2 is 8. So the size of the number is the same, but we've got a negative times a negative, that makes it a positive, but we're going to multiply it by a negative once again, which turns it into a negative once more. So negative times negative times negative is still negative. We've got a -8. So we get the same quantity. We've got an 8, but we've got in one case a positive number and in the other case a negative number. So if we put in a +2 here, we would end up with a y height of 8 over here. And if we put in a -2, we would have a y height, or if you like, a y depth of -8 over here. So we've got, in both cases, the same distance, 8, from the x-axis, but in one case, the value is positive, in the other case, the value is negative. So we've got symmetry, and it's a perfect matchup in every respect except one. The sign has changed. So the way we express this is, well, for an odd function, of course, f of x is going to be f of x. But f of -x is going to equal negative f of x. that means we're going to get the same value, an f of x, from the same function, but if the input is negative, the output is also going to be negative. So if we put in the same x value in positive and negative forms, we're going to get the same output in positive and negative forms. Now, looking back at our first page, we see that we've got, indeed, odd functions in all the other cases. In this case, if we put in a positive 1, over here, our y height would be positive 1 plus 1. If we put in a negative 1, our y height would be negative 1. And over here, it'd be the same thing. If we put in a positive 1, we would, in this case, we'd simply change the sign. Negative positive 1 would be negative 1. So down here would be at negative 1 if we put in a positive 1. And if we inserted a negative 1, we would get a y height of plus 1. So this is indeed a odd function because f of x is simply what it is. But if f of negative x will give you the same result, but with sign reverse, is negative f of x. And we already went over the example of x cubed, and the same thing is going to happen with negative x cubed. We know that that x squared looks like this, and we know it's an even function, but this is going to be true of x raised to any even power. For example, if we had x to the 4th, x to the 10th, x to the 500th, it would still look pretty much the same. I mean, it would be a little bit wider, but it would be the same U-shaped even function. And if you raise x to any odd power, x to the 3rd we saw, but let's say if it was x to the 5th or x to the 111th, it would still look pretty much the same. It'd be a bit steeper as you made the power greater, but it would still be the same kind of an odd function. So if you've got a really simple function like x to an odd power or just x to an even power, you can tell just by the number of the power, whether it's odd or even, whether you've got an odd or an even function. But the question arises, well, supposing you've got something which isn't just an x to a power, supposing you've got something like x squared plus 3x minus 1. Is that odd or even? Well, you could put it in your calculator, but even if you did that, you might not be able to see everything that's happening. For every number, for example, if you put this in, let's see what that would actually look like. I'm going to put that in my calculator, and I get a graph that looks like this. And we can just by eyeballing it, we can see that this is not symmetric around. We can also see that it's not symmetric around the origin, because if we took this half of it and we flipped it over and then flipped it again, it clearly wouldn't match this half. But there are all kinds of graphs. Supposing we got something which, in the little square that we can see on our graphing calculator, looked nice and even, but actually behaved really weirdly as it went off in other directions. We couldn't tell just by having a look at it. So what we would do is we would substitute some numbers to see what we have. So let's try a simple one. Try f at 1. And that would give us, in this case, 1 squared plus 3 times 1 minus 1. That would be 1 squared is 1 plus 3 times 1 plus 3 minus 1. So 1 minus 1 is 0 plus 3, so that's going to equal 3. Now, if I put in f at negative 1, well, then I'd have negative 1 squared plus 3 times negative 1 minus 1. So negative 1 times negative 1 would be 1, plus 3 times negative 1 would be minus 3, minus 1 would be minus 1. So 1 minus 1 would give us 0, but then we'd get a negative 3. So it looks like we actually have here something that's symmetric around the origin. Is that really true? Well, let's try something a little bit bigger. Actually, let's clean this screen off a little bit so we can see what we're really playing with here. But let's try another number. Let's try f at 3. Now, this is still our function. Our f of x is equal to x squared plus 3x minus 1. So that would be 3 squared plus 3 times 3 minus 1. So 3 squared would be 9, and 3 times 3 would be plus 9, plus minus 1 would be minus 1. So 9 plus 9 is 18, minus 1 would be 17. Now let's try a negative 3. F at negative 3. That would be equal to negative 3 squared plus 3 times negative 3 minus 1. Now negative 3 times negative 3, that's this part, would give us a positive 9. 3 times negative 3 would give us a negative 9, and negative 1 would be a minus 1. So 9 minus 9, those two would cancel each other out. We'd have nothing left but a negative 1. So we'd get here a negative 1. So when we tried another number, a slightly bigger one, we saw that we got actually two different answers. If this was an even function, we would get the same outcome in both cases. If it was an odd function, we'd get the same quantity with different signs. But what we got instead was we got different quantities and the same sign. So this function is not even and it's not odd. We saw that right around here where we have an x value of 1 and an x value of negative 1. It looked like it was an odd function. We got now a result of 3 and negative 3. But when we tried a slightly bigger number, we got really, really different results. We got 17 and 1. So it's not odd or even. The question is, how can we tell if a function is odd or even anywhere on the graph? Not just the convenient part over here where we can see it in our graphing calculator and we can try some really small numbers which are easy to work with, but how can we tell what happens as we go off towards negative infinity or positive infinity, as we start using really big numbers? In that case, we're going to have to use algebra because we could just try a couple of points, and if we're lucky, we'll get the results that we want and we'll be able to find out whether it's odd or even. But how can we be sure that in all cases it's always odd or even? How can we really tell for dead sure? That's going to take a little more algebra, and that's what we're going to look at in the next video.